There's loads of reasons for resolving a force. Resolving a force means not splitting it up into individual parts, but sort of identifying the extent to which it goes one way and the extent to which it goes another way if it goes both of those ways. So if I'm going diagonally up here, I'm both going that way and going that way. And it's what you're doing when you're resolving forces is you're working out the extent to which it does each of those things. Now, why would we do that? Millions of reasons. Usually for your purposes, what you're going to be doing is finding resultant force. And that may or may not be because you're going to use Newton's second law. That the sum of the forces is the mass times the acceleration. So in order to calculate the sum of the forces in a particular direction, then you need to know how much force you have in that direction. So for example, here, I don't know how much net force, resultant force I have left and right, because I've got Q going right and I've got this diagonal 8, which a bit goes left and a bit goes up, sort of being pulled in both those directions. Similarly, I don't know how much up and down there is because this 8 is pulling up a little bit, but not 8. So that's what resolving forces does. What you do is you get your pen and you create a right angle around your force. Okay, it doesn't matter. You can navigate that right angle however you like, so long as that your force is in the middle of it. So usually we are going vertical and horizontal, so that's parallel to the x-axis and parallel to the y-axis. Or if we've got something on a slope, then we might be going like this, so parallel to the slope and perpendicular to the slope. It doesn't matter, but you need to be creating a right angle, and that right angle must contain the force. So for example, I will show you going left, right, up, down for these ones. So I would go that way and that way. I would go that way and that way, that way and that way, and that way and that way. That's the first thing. Now, the more difficult bit is this, that you need to chase your angle around the diagram. So I'll give you the example with this one. If I put the weight going straight down towards the centre of the Earth, now I'm going to put my forces on. I'm going to use a right angle either side of the force like this. And now I need to find out where this alpha is inside here. So which of these angles do I know? Because that's going to dictate which of these is cosine and which of them is sine. Now, it's not a rule, because if you know that one, then you equally know that's 90 minus it. So you know both of them, but it's sometimes easier to just use the same alpha that you've got in the question. So for example here, that alpha, if you work out what this is, this would be 90 minus alpha, because this is a right angle triangle, and then this is a right angle here. So that angle in there is 90 minus this angle, which is alpha. Okay, so that angle is alpha. Now, the reason I drew this in pencil is that sometimes it really helps if you have your diagonal force in pencil, and then what you can do when you've resolved the forces, you can then rub it out, and then your diagram is much, much cleaner. You haven't got forces all over the place that actually you've already resolved into the other forces. So I've still got the weight on, I've just split the weight up into those two bits. So I'm going to put this weight on, but just with a dotted line, and you can choose what you think about whether or not you think it's clearer if you rub it out or if you leave it on. Now, let's say this is alpha. Let's say this is alpha. Obviously, it depends on the situation. It depends on the diagram, which one's alpha. The one that is next to alpha is the cosine. Another word for next to is adjacent, and the cosine is the adjacent over the hypotenuse. I was just choosing what letter to use for my force. I think the length of this force is going to be F, since it's a force. But obviously in this case, it wouldn't be F, it would be mg, because it's the weight. So the one that is next to the alpha is there. So this one would be mg cos alpha. Always, when you're resolving the weight, that's always mg cos alpha, going like that, perpendicular to the plane. And the other one is mg sine alpha. So the other one is sine alpha. So you only need to remember one of them. The one adjacent to alpha is f cos alpha. So this one, f cos alpha. This one, f cos alpha. That one, f cos alpha. That one, f cos alpha. And then the other one is f sine alpha. So really, this is the hardest thing, is working out where alpha is. Okay, what else? There's situation which I will tell you about, which is worth remembering, but I'm going to go through these 3 examples. And I don't normally do 3, especially not split up like this, but I wanted you to see that they look very, very similar, but they're actually completely different in the way that you would approach them. So it's a good example of the sort of different approaches that you would take when you've got this sort of problem. Right, in this case, we've got equilibrium. That is very, very important. If we've got equilibrium, then we have no net force. And if we have no net force, then we have no acceleration in any direction. And if we have no acceleration in any direction, then the sum of the forces in any direction is 0. And that's in any direction. So I'm going to use that information and say that all of the forces left and right must equal 0, and all of the forces up and down must equal 0. But to do that, I need to resolve this 8 force. So I'm going to squash that one in there next to the 5. So split it up. This one is adjacent to next to the 30, so that's 8 cos 30. This is the other one, so that's 8 sine 30. Now this is where you can think about, would it be nicer if I could now rub out that 8 and just see everything going left and right? Okay, we're done. So all the left equal all the right, because there's no net force left and right. So Q is 8 cos 30. And all the ups equal all the downs, because there's no acceleration in this direction either. So P equals 5 plus 8 sine 30. So that's 9 newtons for P and 6.93 newtons for Q. Easy peasy. Right, these 2 are going to be a little bit more tricky. This one we've got to draw the picture ourselves. So we've got 2 forces and they are acting on a particle, and P acts north. So that's very easy. There's P and there's the particle. Now, we're not told about Q, but we are told about the resultant of P and Q. So that's where you add them up, or vector-wise, you put one on the end of the other one. So if I do P and then I do Q, then this is where I'm going to end up. So the resultant of P and Q is a force magnitude 10, bearing 120. So it's going to be going like this. This is P plus Q. So that means that Q must look like this. Now, normally we draw the force coming out the particle, but here I've done the resultant of the 2. So I've put Q on the end of P. That's P there. And then this is 120. And this is the resultant P plus Q, which has a magnitude of 10, and P has a magnitude of 7. Okay, there's the picture. Now we're asked to find the magnitude and direction of Q. Well, obviously it's just going to be the cosine rule, isn't it? This is just like just staring us in the face cosine rule. So length of Q squared is this squared plus this squared minus 2 this cosine that. So 7 squared plus, I can do 10 squared in my head, well done me. So Q, the length of Q is the square root of 219, which is 14.8 newtons, 3 significant figures. Right, what about the direction? Give your direction as a bearing. Now look at Q. Let's draw another picture here. Here's Q going off that way, like that. This is north, and that is the angle that I want. That in there is the bearing. Okay, let's put the rest of the information on. I know that if I join... maybe I've put too much information on. No, it's okay. I thought I was going to overlap this, but I won't. It's okay. So if we keep coming down here, and that's where the particle is there, and there's that resultant, P plus Q, and this here is 120, and we know the length of Q now, it's 14.8. Well, actually, I don't need the modulus on. Q is 14.8, and we know that this down here is 10, and we know that this here is 7. So I'm going to get this angle, and then I'm going to do 180 minus to get the bearing. How am I going to get that angle? Sine rule. Cosine rule, sine rule. So the sine, I'll call it theta. The sine of theta divided by 10 is equal to the sine of 120 divided by 14.8. Okay, so if we do sine 120 over 14.8, I shouldn't really do a rounded version here. I should go back to root 219 just in case that premature rounding causes a problem, and then multiply it by the 10, and then we get what sine theta is. Okay, let's do shift sign and find out what theta is. Okay, 35.8. Okay, or is it? And this is a very, very important thing to remember. If sine alpha is something in a triangle, then the alpha, I'll put in a triangle because that's important. Then when you do shift sign, then the calculator assumes that you want the acute angle, not the obtuse angle. But angles in a triangle can be obtuse, and the angle we're trying to get might be obtuse. So if you do shift sign, or arc sine is the better way of putting it, if you do arc sine of that, then you will get an acute answer. You might want the obtuse answer. So it might not be that this angle is 35.8. It might be that this angle is 180 minus. It's the other one, the second solution. Now, luckily, I've got my picture here and I can see that it's an acute angle. This is 120. I can see that I definitely do want that one, but just beware of that sign inconsistency inside triangles. Students often just go shift sign, that's what it is, and no. If it was an obtuse angle, then it's 180 minus that. Now, the bearing is a three-figure number starting here, going round, so it's going to be 180 minus this answer, which is 144. So the actual bearing is 144 degrees. Okay, totally different approach. Cosine rule, sine rule, resolve the force and go up and down. Let's have a look at this one. This looks very much like that, like we're going to resolve the forces. Okay, so we've got equilibrium again. So that means no net force, no acceleration in any direction. The sum of the forces is 0. Find F and X. So this time we're finding out two things instead of one thing, but the same principles apply, which is that we can resolve this F force. This is adjacent, so this is F cos X, and this is the other one, so this is F sin X. Imagine rubbing that out, and then you can see all the forces, and then what we know is that 6 equals F cos X, and 5 equals F sin X. Now we need to do simultaneous equations, so I'll put this one on top of that one. 5 over 6 equals, well, if I put that on top of that, the F's will cancel, and the sine over cos can be written as tan, and then I can do shift tan, arc tan, and get alpha. Okay, so alpha is, not alpha, X, the angle, 39.8. Right, now I need to go back into one of these, so maybe I'll take the first one. 5 equals, and I now know what the X is. So I need to put the X in there, but important thing, okay, if you know any trig ratio, you can get the other trig ratios exactly. So if you know sine or cos or tan, then you can get the other ones without using the calculator. And quite often this is what you're going to need to do. Now I could get the calculator now, and I could do 5 divided by sine of 39.8. And I will get what F is, 7.8, but I'll get what F is in not exact form. And it may well be that you need the exact form. So this little trick is very, very important. So in our case, we know tan. That's common that we know tan. Draw a little triangle and put on what you already know. So I know that tan X is 5 divided by 6. But tan X is the opposite over the adjacent. So the opposite must be 5 and the adjacent must be 6. And therefore the hypotenuse is that squared plus that squared square rooted, which is root 61. So now I know sine X. For example, sine X is 5 over root 61. And that's the exact value of sine X. So I'm going to put that there, the exact value, rather than putting 39.8 in. So 5 divided by 5 over root 61 is F. So F is root 61. And root 61 is, yes, thank you, calculator, is 7.8. 3 significant figures. I nearly forgot newtons. I squished in the newtons there. Right, now I want to show you quickly, as a final thing, a much, much, much easier way of doing this. Now you can only do it when you've got equilibrium and you've got 3 forces. When you've got equilibrium and you've got 3 forces, then you can use a triangle of forces. And this comes back to what we were talking about here about the resultant of the two being what happens when you put them on the end of each other. Now, if we have 3 forces and equilibrium, then if we put these forces on the end of each other, then they will come back to the beginning because there is no net resultant force. Let's put them on the end of each other. Let's do F first. Now let's put 6 newtons to the left on the end of F. And now let's put 5 newtons down on the end of 6. So the resultant force here is 0 because the 3 of them all cancel each other out. Now you have a look at that and you work out how easy it's going to be to find the F and the X. Here's the X down here. Okay, it's just going to be ridiculously easy. This is a Z angle, what's it? So that's X there. So I can literally just write down straight away, tan X is the opposite over the adjacent. And I can see that F is going to come from Pythagoras. F is 5 squared plus 6 squared square rooted. Easy peasy. So that is all of it. How do you do it? And then don't forget cosine rule, sine rule, triangle of forces if you've got 3 forces in equilibrium. Draw pictures, and practice, practice, practice.